everyone, welcome back to the channel. In today's video, we'll be learning about a deep learning fundamental that is gradient descent. We'll be covering on the introduction to what exactly is meant by or defining gradient descent. Post that, we'll be covering the key characteristics of the gradient descent. Namely, the first one is loss function. The second one is what exactly is meant by gradient. The third one is learning rate. Post that, we'll be delving into what are the steps essentially in gradient descent. How do we get to the minimum loss function? And lastly, we'll delve into a mathematical explanation of the steps in gradient descent using a example. Let's start by defining what exactly is meant by gradient descent. So gradient descent is an optimization algorithm used to minimize the function by adjusting its parameters. What exactly is meant by a neural network, or why do we train a neural network? The main objective of training any artificial neural network is to have good predictions or valid predictions with respect to any business use case. To achieve that, we train that particular model using historical data. In the training process, the only objective that we want to optimize for is that the predicted value, that is y hat, the predicted value of the particular model while training is as similar to the original or the actual value or the target value, correct? That is the difference between y actual and y hat, that is the predicted value, should be minimum. The basic fundamental of a artificial neural network, fundamental unit of a artificial neural network is a artificial neuron. The parameters that define the output of any neural network or an artificial neuron, these are the two basic or the major parameters, which is the weights and the bias. To learn more about weights and bias, please refer to my video on neurons. So these are the two parameters which define the output or the predicted value, that is y hat. So gradient descent is the optimization algorithm to minimize a function. Over here, the function is to minimize the difference between y and y hat, that is the actual value and the predicted value, by adjusting the parameters. What are the parameters that we are interested in? Majorly the weights of the artificial neuron and the bias of the artificial neuron. So this is what is meant by the second statement. In context of neural networks, it helps us find the values of weights and also biases that minimize the loss function. The function that we are trying to minimize, the loss function, is y minus y hat. That is the difference between the actual value and the predicted value. This process helps us measure how well the network's prediction match the actual data. That is, the y and y hat should be as close to each other as possible. This is what is meant by the whole process of gradient descent, making the actual and the predicted value as close to each other, so that in the future, while solving any business problem, after we have trained that particular model, it performs good on the unseen data. So there are three major characteristics that define the process of gradient descent. Namely, the first one is the loss function. The second one is the learning rate, that is this incremental steps, also known as the learning rate. And the third one is gradient, that is this particular slope that you see, also known as the gradient or the slope. We'll check out each of these, learn about these in depth going forward. Let's start by defining the first characteristic of gradient descent, that is loss function. Loss function is also known as the cost function or the objective function. The goal of training any machine learning model or deep neural network model is to minimize this particular loss function. What is essentially meant by loss? Loss means the difference between the actual value and the predicted value. What's the difference between these two? The less the difference, meaning the model is training well, and the more the difference, it needs to be trained even more, so that this particular loss function can be minimized, so that the actual value comes closer to the predicted value by the model. This helps in improving the accuracy of the model's prediction and getting us close to solving the business problem at hand. myriad functions, that is algorithms in machine learning and deep learning methodologies, have their own loss functions. For instance, if we were to solve any regression problem wherein we the objective of a regression problem is to find the best fit line. For instance, this is the model's prediction, the line that I am highlighting in red. This is the model's prediction, that is the y hat, the predicted value, and all the blue lines, blue points over here are the actual values, that is the y. So over here, the heights that you see over here, either in the positive direction or the negative direction, are the errors. That is the difference between y and y hat, that is actual and the predicted values. In linear regression, we have many loss functions. One of the major loss functions that we try to minimize is the mean square error, wherein we find the difference between the y actual value, that is y I, and the predicted value y hat I for each of the observations. So we have multiple observations over here. We find the difference between actual and the difference at each and every for each and every observation, square that for each and every observation and do a summation, right? At the end, we do a mean of that. Hence, the name mean square error. For us to optimize the regression model, we need to minimize this particular loss function, that is mean square error. This mean square error is the loss function with respect to a linear regression model, which we need to optimize so that we can improve the accuracy of that particular model, bringing the actual value closer to the predicted value. So let's try to understand the second characteristic of gradient descent, that is the gradient of loss function. The gradient of loss function with respect to weights and biases of a neural network tells us the direction and rate of change in the loss. As we have already discussed, the objective of any model is to minimize the loss function, that is the gap between the actual and the predicted value. Let's take an example that on the y-axis we have a loss and this parabolic curve is our loss function. What we want to achieve is we want to go till this particular point where the loss is minimized, right? To go to that particular point, let's say we are starting from this particular point. How do we decide in which direction to move so that we reach this particular point? This is where gradient of the loss function helps us. That is, it points us in the direction of the steepest increase in the loss function. To minimize the loss, we move in the opposite direction. To help you understand with this particular example, we want to move from this particular point to this particular point. What we do is we first plot a slope. We draw a tangent at this particular point and check out the slope. Slope also means the gradient. Both are synonymous. At that particular point, we plot a tangent and get the slope. Let's say we have a positive slope over here of plus 60. What this says is we, to minimize the loss, we move in the opposite direction of the gradient. So since it's a positive 60, we move in the opposite direction, reducing the slope. That is, we move from this particular point to this particular point and we plot again a slope. On this particular point, let's say we have a slope of from 60, it reduced to 40. Again, we move to this particular point and plot the slope. Again, from this point to this particular point, we see that the slope reduced to 20. And gradually moving in the opposite direction, reducing the slope, the positive slope that we had, we'll reach to this particular point, right? Where the slope is 0 and the loss is minimized. Similar, if we were to start with this particular point, we would go in this particular direction one by one in the opposite direction of the initial slope and reach to a point where the slope becomes 0 one by one gradually and the loss function is minimized. So how do we find the slope at each and every point so that it points us to the right direction? It is calculated by the partial derivative of the loss function with respect to each parameter in the model. Mostly we do it using weights and biases, which are the major parameters in a neural network. We do a partial derivative with respect to each of them because derivative is a function which helps us find the slope at that particular point and hence guides us to the direction to minimize the loss. This is what is meant by gradient of the loss function. Coming to the third characteristic of the gradient descent process, that is the learning rate. Learning rate is a small positive value that controls the sizes of the steps that the model takes to reach the minimum of the loss function during the whole training process. It also determines how quickly or slowly the model updates the parameters, that is, the weights and the biases, in the response to estimated error each time the model weights are updated. So, as we discussed, the objective is to minimize the loss function that remains constant. We saw how gradient helps us determine the direction in which we want to move so as to minimize the loss function. For instance, if this is the point that we start from, this is the direction that we need to take to reach this particular loss, the minimum loss, right? The gradient helps us decide which direction to move. But the steps that have to be taken, let's take an example. Over here is the starting point, and we want to go to this particular point. This is our objective. The steps, the sizes of the steps to be taken to reach this particular point is decided by learning rate. For instance, if my learning rate was less, let's say it was 0.001, the step size would be small. Let's say it would go to this particular point, reevaluate, then go to this particular point. The step size is smaller. It will take more number of steps to reach this particular point, right? This is what is meant by a smaller learning rate. For instance, now if I update the learning rate from 0.001 to zero point 0.2, which is a high learning rate, the sizes of this step would increase. The time it would take for the model to reach this particular point, the slowness that we experienced initially with respect to a lower learning rate will become less as the step size would increase and will reach to this particular point earlier. This is what is meant by learning rate. It decides the step or the rate at which the model tries to descend the loss to the minimum. That is, we want to reach to the minimum loss of that particular loss function. It decides the sizes of the step or how quickly the model reaches that particular objective, right? If the learning rate is too high, the algorithm might overshoot the minimum, right? What does this mean? For instance, on the left hand side, this particular graph, if we have a bigger, very big learning rate, there is a possibility that the model has such big step size that instead of going from here to here, it might overshoot and go into the opposite direction, which is not recommended. The second point is if the learning rate is too low, the convergence might be too slow and there is a risk of getting stuck in the local minima. So over here, if the speed at which we were going is too slow, that is the learning rate is very, very slow. Let's say it is 0.000001. The step size would become very, very small. That is, it will update very less in the course of action to reach that particular end minima. The step size would be very small. Hence, the convergence to this particular point will take a lot of time, and there is a possibility, a risk of getting stuck in local minima. What is local minima? If we see this particular graph on the lower side, that is this one, this is called as a local minima, and this is called as a global minima. So over here on the y-axis, we have the loss function. This is a loss function. On y-axis, we have the loss. So we want to reach, let's say we are starting at this particular point. The objective is to reach this particular point. That is the global minima. That is minima with respect to the overall graph or overall loss function. We want to reach over here. But let's take an example. If we have a very small learning rate, if the size of each step converging to the lowest point is very small in this particular fashion, there is a chance that the model gets stuck and assumes that it has reached a minima that is local to this particular area, right? This is a problem of very small learning rate wherein the model converges to a local minima to this particular area and overlooks the global minima which it has to reach. So the point over here is we have to optimize the learning rate so that it's not at the either extremes, neither it's too high, neither it's too low. It's an experimental value that it has to be in between so that the model reaches to the global minima in each case. Now coming to the steps that are involved in gradient descent algorithm so that we achieve the lowest possible value of the loss function. The first step is we initialize the weights. We start with random value of the weights or the parameters, that is bias or the weights in the neural network. The second step is we compute the loss. That is, with one forward propagation, we have a logit, that is an output. We compare it with the actual value, that is y hat minus y. We compare the loss. This is the loss. We calculate the loss with respect to the current initialized random weights. The third step is to calculate the gradient. We compute the gradient of this particular loss, that is using a derivative. We try to find the direction in which we need to go to minimize this particular loss. Now, the fourth step is in the backward propagation, we try to update the parameters, that is the weights and the bias of that particular neural network. We try to adjust the weights in the opposite direction of the gradient by a small step. That small step is decided by the learning rate, right? Then the fifth step is to iterate or repeat this process over and over till we converge to the minimum value of loss. Let's try to understand this whole process using an example. The objective of this particular example is to find the value of w such that it minimizes the function f of w. That is, we want to find the value of w such that this particular loss function f of w gets to a minimum point. Since this is a very easy function, we can see clearly that f of w's minimum value will be 0 and it will be achieved only when w is equals to 0. Let's try to see how do we reach this particular point using the process of gradient descent. The first step in our process that we just saw was randomly initializing the parameters. Since we have the parameter as w over here, we are randomly initializing it to w equal to 2. The second step over here is to get the derivative or compute the gradient so that we get the direction in which we have to move to minimize the loss function. The derivative of w square hence would be 2w, which is our gradient. The third step in the whole process is updating the parameters. The parameter that we want to update over here is w. We update it using a product of alpha, which is the learning rate, and the derivative of the function, loss function, that is the 2w, right, which is essentially our gradient. And this particular minus sign signifies that the direction in which the opposite direction of the gradient is where we want to move to minimize the loss function. Hence, we are updating the parameters in the opposite direction of the gradient as we saw earlier. Alpha over here determines how quickly or slowly would the parameters update. If alpha had a greater value, this whole function over here on the right side of subtraction would increase and the weights would or the parameters would update quickly, whereas if alpha were a smaller value, this particular subtraction or updation of the parameter would become a bit slower. This is what is meant by the step size or the learning rate. Coming to the fourth point, wherein we want to iterate over this process, repeat it till we converge to the lowest minimum possible value of the loss function. Let's try to understand this mathematically now. Over here, we'll see a few mathematical iterations of the earlier process that we saw. In the first iteration, we initialize the weight to 2. Then we calculate the gradient. The gradient is essentially f dash of w is 2w. Hence, the formula 2 into 2, that is 4, is our gradient. We update the weight, that is w equal to w minus alpha of f of w. Right? This alpha is the learning rate. We initialize this learning rate to 0.1. Hence, we have the formula that is initial weight w minus, with the initial weight over here 2, minus the product of learning rate and the gradient. Gradient comes from here and the learning rate is what we have defined. So we have the new weight or the new parameter as 1.6. Then we come to the second iteration. Now, since the weight has updated, we have the updated weight as 1.6 and we repeat the same process of calculating the gradient with respect to that. That is 2 cross 1.6, which gives us a value of 3.2. We update the weight again with this particular formula, that is w, that is updated weight 1.6 minus the product of gradient 3.2 and the constant learning rate, which gives us a even lower weight parameter, w parameter, as 1.28. The third iteration, we have the updated weight as 1.2 over here, 1.28. We again calculate the gradient, that is 2 cross this particular weight, that is 2w, and have this particular gradient as 2.56. updating the weights using that is our weight minus the product of learning rate and the updated gradient, which we come across as 1.024. Repeating the same process in the iteration 4, we see that the weight now has decreased to 0.8192. If we were to repeat this process again, we see that the W is approaching zero step by step. And let's say till 10th or 15th iteration, it will reach to a point where W will be approximately equal to zero, following the same iterative process. And that particular value of zero, approximately zero, will give us the minimum value of f of W, that is equal to zero. This is the process of gradient descent one by one till we reach the minimum value of our loss function.
Please do not forget to like the video and subscribe to the channel for more such informative videos related to artificial intelligence. Thank you.